Hi everyone, Dr. P here, and in this lecture we're going to look at electromagnetic radiation, or light. Now we're starting a new chapter on atomic structure and the periodic table, and there's kind of two themes to my lectures here. A lot of them will be on the nature of the atom, that is the modern version of the nature of the atom, the structure of the atom. And then we will spend some time talking about the periodic table, which is a periodic repetition of chemical properties among elements. And we'll see that the periodic table not only is arranged by properties, but also by the structure of the atom. And we can see how if you forget the periodic table, but you remember some of your rules of atomic structure, you could regenerate a periodic table. Or if you forget your rules of atomic structure and you have a periodic table, the periodic table can remind you about the features of modern atomic structure. But let's start off by looking at electromagnetic radiation, EM radiation. And electromagnetic radiation is light, and it's a form of energy. In fact, a lot of times I'll use light as a word for electromagnetic radiation. X-ray, UV light, ultraviolet light, X-ray light, etc., infrared light, where perhaps saying radiation might be more appropriate. But anyway, some properties of light, electromagnetic radiation. They propagate or travel at the speed of light in a vacuum. And we denote the speed of light with the lowercase c. That's the constant. Let's see. Well, it is constant. The speed of light in a vacuum. Speed of light in a vacuum. And then also light will exhibit wave-like behavior. So now what does that mean? Well, let's take a look at waves. Waves are characterized by several things. We have wavelength, which is denoted with a lowercase Greek lambda, which is the distance between peaks. We also have frequency, which is denoted with the lowercase Greek letter nu. So let me try to draw this a little bit better here. It kind of looks like a sort of slanty V, if you will, sort of a slanty pointy V there. And this is the number of waves per second. So a number of waves that go past a point per second. Sometimes called cycles per second. We also have the speed, which is constant for electromagnetic radiation. So we'll just leave that as c, the speed of light. And then we have amplitude, which is the height of the peaks. Oops, so if I can spell height correctly. So let's focus on these three here. And we'll take a look. So speed is constant, and frequency and wavelength are inversely proportional. So long wavelength goes with lower frequency. if you think about that, that makes sense, because if our light has a fixed speed, a constant speed, that means that longer waves the peaks will be, that are farther in between, they will pass more slowly by a certain point, even though the overall light wave propagates at a constant speed. Conversely, short wavelength corresponds to high frequency. So notice the inverse relationship. So we could also state this as lambda, having trouble with my Greek letters today, lambda nu equals C. And then units of frequency are cycles per second, or 1 over seconds, reciprocal seconds, or seconds to the minus 1, or hertz, capital H, lowercase z, named after a scientist by the name of Hertz, who did a lot of work with electromagnetic radiation back in the early 1900s. All right, so remember this, lambda nu equals C. We will run across that a little bit later. Okay, now let's take a look then a little more closely at the electromagnetic spectrum. Because we'll be talking about parts of this spectrum in more detail in this chapter. So let's draw out a big long line here, and then okay, and so this is going to be our wavelength in meters. So we'll have wavelength in meters. So really short, 10 to the minus 4, sorry, 10 to the minus 12, I can't read my own writing here. 10 to the minus 12 is gamma rays, so high energy radiation. 10 to the minus 10 meters is X-rays. 10 to the minus 8 meters is UV. And then we've got a region between 4 times 10 to the minus 7 and 7 times 10 to the minus 7, which is our visible. I'll expand that in just a minute. We can continue on. We have 10 to the minus 4, which is the far IR region. 10 to the minus 2 meters are microwaves. I'll just use the Greek letter mu to represent the word micro. We have 1, we could have 10 to the 2, and 10 to the 4, and this is the region of radio waves. And radio waves have, on the shorter end, are FM, and then in between, we have shortwave, and then AM are longer. Now let's look at our visible region here. So I'm going to go ahead and expand my visible region. So we have 4 times 10 to the minus 7, one end, and 7 times 10 to the minus 7 on the other end. And then we'll have 5 times 10 to the minus 7, 6 times 10 to the minus 7. And so this is our visible region here. And so we have our spectrum here, where we've got violet with the shortest wavelength and highest energy, followed by blue, then green, yellow. I don't have a yellow pen, unfortunately. Orange, and then red. And this is, of course, letters from the mnemonic Roy G. Biv. Where'd the I for indigo go? Well, there actually isn't really an indigo. And again, this is a continuous spectrum. Indigo is in between blue and violet, and Isaac Newton put it there because he thought there should be 7 colors in the visible spectrum. 7 being a lucky number and everything. But so you can still remember Roy G. Biv or Roy G. Biv if you want to. But those are going from longer wavelength to shorter wavelength. And I've drawn things going in terms of energy. And traditionally, when we draw out spectra like these, we put the higher energy stuff on the left and the lower energy on the right. So we'll talk much more about the visible spectrum, or not so much the visible spectrum, but we'll talk about how atoms interact with visible light later on. All right, well, until then, stay safe out there. Bye now.